that is mixture designs. So today we will start with the mixture designs. Commonly, we are using two mixture designs, that is simplex lattice designs and simplex centroid designs. Now let us discuss an example where we need to utilize the mixture design and why we cannot use the conventional designs. There is either full factorial designs or central composite designs or box Benton designs. So for an example, if you are preparing a lemonade and you are using lower levels and higher levels of sugar and lemon. So if you use one lemon and one cup of water, lemon and water, one lemon and one cup of water, the ratio will be 1 and taste is good. If you take 2 lemon and 1 cup of water, the ratio of lemon to water is 2 and taste will be sour. If you take 1 lemon and 2 cup of water, the ratio of lemon to water is 0.5 and the taste will be weak. Again, if you take 2 lemons and 2 cup of water, the ratio is 1 and taste will be good. Now, if you look at this design, it is a 2:2 full factorial design, in which one of the factor is lemon, second factor is the quantity of water. But when we are using both of them at lower levels as well as at higher levels, the result is same. That is, we are getting the same taste, because over here the result is not dependent on the absolute quantity of any excipient, but it is dependent on the ratio of lemon to water. The similar things happen when we are preparing emulsions. You might have prepared emulsions and studied emulsions in your dispensing pharmacy practicals, in which you studied, I think, that the ideal ratio of the emulgent to oil to water is 1:2:4 in some cases. Okay, sometimes 1:2:2, etc., etc. So that is ratio. That ratio is important. Now, if you are preparing emulsion using, for an example, 5 ml of water, 5 ml of oil, and 2 grams of the emulsifying agent, the same results will be obtained when you are preparing an emulsion using 10 ml of water, 10 ml of oil, and 4 grams of emulgent. Again, using 20 ml water, 20 ml oil, and 8 grams of the emulgent. So in all these experiments, we are changing the quantity of individual excipients, but end result is same, because the end result is dependent on the relative proportion, the ratio, and not the absolute quantity. Another thing, when we change the water concentration, that is amount of water, rest two excipients are by default affected. Their quantity, their ratio changes, not quantity, but the ratio changes. Similar kind of experiment you performed, I think, using the ternary plot. You might have studied the acetone, water, and benzoic acid system, or acetic acid, benzoic acid, acetic acid, and water system, in which we are using acetic acid as a bridging liquid that will help mixing water and benzoic acid, which are actually immiscible, and we are increasing the concentration of the bridging liquid to get the ratio where all the three phases get mixed up. Okay, we get a single phase. So all these are examples of the mixtures in which relative proportions are important and not the absolute quantity. And in such cases, we must use the mixture designs. With this note, let us move ahead. So here we can see, as in run 1 and run 4, both factors, both experiments show the same taste, and because the ratio, relative proportion, is important and not the absolute quantity. So it makes more sense to look at taste as a function of proportion of lemon to water and not the amount. So the mixture designs, they account for the dependence of response on proportionality of the ingredients, not the quantity of ingredient, but proportionality of ingredients. So in mixture designs, when we have independent factors, the factors are always proportions of different components of a blend. If we are using, for an example, two factors, x1 and x2, then the relative proportion of x1 and x2, or percentage composition, will always add up to 100 if you are using 3, 4, anyone. But the total is always 1 or 100%. So either they are represented as percentage of total composition or as a fraction of total composition. And the total summation of x1, x2 and x3 will always become equal to 1. Now, in conventional designs, it is not that the case. In that, we are using 0, 0 levels as well, 1, 1 level as well, 0, 1, 1, 0, minus 1, etc., etc. And so, the total ranges from some negative value depending on the number of factors. Say we are using 2 factors, then this total may be -2, -1, 0, 1, and 2. Can assume all these values. If we are using 3 factors, it can assume the values ranging from -3 up to +3. Okay, but over here it is not possible. The summation of all the factor values levels will always become equal to 1. The total of all the levels will be always become equal to 1 or 100%. Now, there are 2 types of mixture designs. First one, that is standard mixture designs, and second one, that is constrained mixture designs. The standard mixture designs are the normal designs in which we do not have any limitations. That is, we are independent to use any concentration or any quantity of all the excipients. Okay, and it may range from 0 to 100 or 0 to 1. But sometimes it is not possible to utilize all the excipients from the entire range. Reason being, there is some limit that you must use any one excipient at minimum 10% level. Okay, so that is a constraint, that is a limit. So this restricts that the maximum quantity of any excipient that can be utilized is 80%, because rest 2 we must use minimum at 10%. So both other excipients can be 10 at lower level, that is 10%, and the third excipient can be incorporated at 80%, up to 80% maximum. If we can utilize both 2 excipients at 0% level, the third can assume 100% concentration. Okay, but sometimes there are constraints, there are limitations that you must utilize one or more excipients at a certain limit. Now this constraint may be upper constraint as well as lower constraint. Anyone may be there. So sometimes you cannot use beyond certain limit, sometimes you cannot use below certain limit. So when these type of constraints are there, we need to construct the designs with constraints. So these designs are also known as extreme vertices design. In standard designs, we have simplex lattice design and simplex centroid design. In constraint designs, the designs are also known as extreme vertices design, though we are using same simplex lattice and simplex centroid, but with some modifications. So here x1 plus x2 plus x3 is equal to 1 or 100%. In standard mixture designs, either we are using 0.5, 0.51 or 0.67, 0, 0.33 or 0, 0.6, 0.4. So any one or more component can be omitted. It can be kept at quantity 0 when we are using standard designs. But when we are having constraints, we cannot omit one or more excipient. For an example, over here, x1 must be used at least 0.1 level. So it is 0.1, 0.45, 0.45, 0.1, 0.1, 0.8. Okay, as I have discussed earlier. So this is a constraint. This is a condition that we cannot use x1 below 0.1 concentration. Now, the difference between independent variable experimental designs and mixture designs is that with the former, that is the mixture designs, the input variables or components are non-negative proportionate amounts. Over here, the levels will range from 0 to 1 and not -1 to 1. This also you should remember. In a mixture design, the levels will range from 0 to 1, not -1 to 1. And that is why the equation for coding of the mixtures are different. We will discuss it, but it's a different equation than which we were using for the conventional or independent variable experimental designs. In that, the equation was actual minus average divided by maximum minus average. Over here, it will be different. Okay, so the values are non-negative. They cannot be negative, and they are proportionate. They are fractions out of the mixture. And if expressed as a fractions of the mixture, they must sum to 1. If they are expressed as a proportion, they must add up to 1. If they are expressed as percentage, they must add up to 100. And the purpose of mixture designs, why we are going to prepare the mixture design. So the purpose is to design a mixture area. If here you need to remember that you will have n minus 1 dimensions. In conventional experimental designs, we are having n dimensions. Okay, we have discussed that for two-factor design, the experimental domain will be square. For three-factor design, the experimental domain will be cubical. Okay, so it is having n dimensions, then n equal to number of factors. So if there are two factors, it is two-dimensional design. If there are three factors, it is a three-dimensional design. In a mixture design, it will have n minus 1 dimensions. So if it is a three-factor design, it will be a two-dimensional design, and the design space will be triangular. Design space will be triangular. Okay. If there are four factors, the design space will be pyramidal, like a pyramid. Okay. So it is n minus 1 dimensions. If there are two factors, the design will be linear. Let me give an example of a linear design. You have, I think, studied the viscosity behavior of a glycerol water system. Okay, you might have studied the behavior of viscosity of glycerol water system using the Oswald viscometer. You are measuring the time required to flow from the upper mark to lower mark of the bulb, and then you are calculating the viscosity. So as the concentration of the glycerol increases, the viscosity increases. Now the mixture contains glycerol and water. Okay, so there are two variables, two factors. One is water, another is glycerol, and we are changing them and we are measuring the viscosity. So this relationship is linear. Okay, you can simply plot it on 1 minute. Wait for a minute, please. Okay, hello. Yeah. So we are having n minus 1 dimensions. The prediction of the response for any mixture or combination of the ingredients can be made empirically, that is mathematically. We can derive the equation as we were deriving for the normal designs. And some measures of influence of each component on the response individually and in combination with other components can be obtained. That is, we can get the coefficients for individual factor, that is x1, x2, x3, as well as we can get the coefficients of the combination, that is x1, x2, x1, x3, x2, x3, etc., etc. Now, assumptions, we need to assume something. So like factorial designs, we are assuming that the errors are independent and identically distributed with the zero mean and have common variance. That is, the errors are on both the sides. Error cannot be on a single side. If it is on a single side, it is not error. Okay, so normally the error should be on both the sides. Another assumption is that the true response surface is continuous over the region. For triangle, for three component, it is a continuous response. That is, that should not be the case where in some point we are not getting response at all. We are not getting any results at all. So your response should be uniform throughout the region. For an example, if you are preparing an emulsion, it should not be the case that using a particular combination you are not able to get the emulsion. Okay, all the combinations which you are using, you should provide at least emulsion. Their properties may differ. That is, the globule size may be different or any other properties may be different, but at least emulsion should be formed. And then the response is assumed to be only dependent on the ingredients proportion and not on the amount of the mixture itself. So it should be dependent on the proportion and not the amount. Now, the objective of mixture design. To find a mathematical model, the equation for predicting the values of response variables, that is dependent variables against its components xi, maybe x1, x2 or x3. And normally they are first order or second degree interactions. The first order or linear equation. Now, another thing you need to mark over here is the equation starts with b1 x1. In conventional designs, we were using the equations starting from b0. The equations were y is equal to b0 plus b1 x1 plus b2 x2 plus b1 x1 x2. Over here, the equation starts from b1 x1. So we are not calculating b0 over here because our factors are ranging from 0 to 1 and the total will always be equal to 1. So we are not calculating b0 constant over here. Then the equation can be linear. That is, it is having all the main effects in interaction terms. The x1, x2, x1, x3 and x2, x3 are called first degree interactions, and x1, x2, x3 is called third degree interaction. Then the model may be quadratic. That is, we are incorporating the square terms, or it may be full equation, which is combination of the previous two. That is, it contains all the terminologies, and b0 is absent. Now, the combinations are prepared in a manner such that the experimental data can be used to predict the response over the simplex space. And the extrapolation to combinations outside the range included in the experimental design is not recommended. We can only claim that the relationship is true within the design space. Outside the design space, we cannot claim that it stands true, but it may stand true, but we cannot claim that. Okay, and we should not rely upon that also. So our response is predictable within that design space only. And one or more extra design points are run as checkpoint bets. Once the simplex design is derived to validate the equation. Normally, in any experimental design, it is required to validate the design. And in order to validate the design, we are preparing checkpoint batches. Checkpoint batches are the batches other than the design batches, at which we are measuring the response, and then we will compare the response obtained theoretically, that is using the mathematical equation, and the practical response. And if they are in agreement, we can say that the design is, the model which we have derived is validated, and it can be utilized for predicting the response over the entire design space. Now, there are two types of simplex designs, like simplex lattice and simplex centroid. So this is a layout of a simplex design in which the pink color points, they are on the boundaries. Points starting from 1 to 7, they are the simplex lattice points, and points from 1 to 10, they are simplex centroid points. Now, point number 1, it represents that x1 is equal to 1. That is, first component, x1 component is at 100% concentration. Point 2 represents the 100% proportion of x2. Point 3 represents 100% proportion of x3. Point 4, which is the center of x1 and x2, it represents the 50% concentration of x1 and 50% of x2. Similarly, 5 and 6 also represent 50-50 proportions. While point number 7 is centroid at the center, and it represents 1/3 proportion of all the components. Now, this boundary which covers the point between the x1 and x2. 1 minute. Okay, this boundary which covers the point between x1 and x2. Over here, in the entire boundary, x3 will be equal to 0. Okay, for the entire boundary, x3 will be equal to 0. Now, if we draw lines parallel to this line, I'm roughly trying to draw it. So, if we draw lines parallel to the line of x1 and x2, the x3 will go on increasing as we move towards the corner of x3. Okay. If we move towards the corner of x3, the x3 goes on increasing. So over here it is 0, over here it may be 0.1, 0.1, over here it may be 0.2, 0.3, and so on. And at this point it assumes the value equal to 1. Clear? Same thing happens for rest of the factors. In this boundary, x2 is equal to 0. And if we plot the lines parallel to this x1 and x3 axis, the x2 will go on increasing. Getting it? Okay. So this is the design or layout of the simplex lattice and simplex central design. x1, that is x2 and x3 in simplex lattice design, it ranges from 1 0 0 0 1 0 0 0 1, then 1 by 2 1 by 2 0 1 by 2 0 1 by 2 0 1 by 2 1 by 2, and 1/3 1/3 1/3. Similarly, for simplex centroid, there are 3 more points, that is 1 by 6 1 by 6 2 by 3 and rest. Okay, so when we are having 10 points, it is simplex centroid. When we are having 7 points, that is simplex lattice. Now, if you are working with the simplex lattice design, we cannot get the idea about non-linearity because we are having less number of factors. And you need to remember one golden rule of experimental designs, that you can analyze maximum n minus 1 coefficients. You can derive maximum n minus 1 coefficients with confidence using any experimental design, where n is the number of experimental runs. If we are performing 8 experiments, we can get maximum 7 coefficients. If we are performing 9 experiments, maximum we can get 8 coefficients with confidence. Okay, more than that we cannot get. So if we are trying to calculate more coefficients, we cannot get the confidence. What is confidence? I will explain when we will analyze the design in Microsoft Excel. Okay, so in simplex centroid, we can get the idea about the polynomials as well. Now, design without constraints in pharmaceutical formula. With constraints, as we have discussed in pharmaceutical formulation, sometimes it is situation where we need to use a fixed proportion or minimum proportion of any excipient. Say some components are fixed and remaining components may be varied, therefore they do not make up to 100% of the mixture. And in addition to the lower limit of varying components, it is often not equal to 0. So in such cases, it is called a design with constraint. We are not able to utilize the range, entire range, ranging from 0 to 100. So such modifications present no problem, and by suitable transformation of the data can be treated exactly same way as the described in the simplex lattice. If it is possible to transform them in a simple way, we can utilize them. The lower limit is assigned the value 0% and upper limit is assigned the value 100%. So if it is possible simply going like this, then we can go with that. For an example, if I am using an excipient at 2% and 10%, so if I am assigning value 2% as 0 and 10% as 1, if it is feasible, then we can do it. Say it's a case study here, an experiment in which simplex design is to be used with optimal properties, and the experiment is prompted by problems with tablet hardness for a large volume marketed product, and the hardness value was found to be dependent on 3 ingredients, namely A, B and C. Now together these components consist of 25% of the original formulation, or 75 milligram. Total tablet weight is 300 milligram, so 25% of the 300 milligrams comes to 75 milligram. Now, a careful evaluation indicated that three components had to be present in an amount equal to at least 10 milligram each in order for the tablet to be satisfactorily compressed. Thus, the recommended simplex design to obtain a satisfactory tablet hardness consisted of varying the three components with constraint, that is a limit. The sum of the component must be 75 milligram and each component be present in an amount equal to at least 10 milligram, not less than that. So now the space becomes 10 milligram, that is 0%, and 55 milligram, that is 100%. Because 55, because we need to use rest two excipient at minimum 10 milligram level. So 10 plus 10, 20 is deducted from 75. So our range is 10 to 55. So the transformation now will take place like this. The equation you need to remember, the equation is different. Over here, it is actual minus minimum divided by maximum minus minimum. In previous experiments, it was actual minus average divided by maximum minus average. Over here, it is actual minus minimum divided by maximum minus minimum. So, actual minus 10 divided by 55 minus 10. So, we can transform in such way and we can construct the design with the constraint. Students, if you have any question, you can ask. So thus, the formulation prepared with 50-50 mixture of the component A and B will actually contain 32.5 milligram of A and B each and 10 milligram of C. Though it is at zero level, but still it contains 10 milligram. Okay. Similarly, the rest of the values can be transformed. So the design will be like this. 55, 10, 10. There is the formulation component and the transformed values are listed over here. Now, here the response is also shown for each design, each run. Here, one more run is prepared for checkpoint to checking the relationship. Okay, this we will discuss in Excel. So, if you have any question, you can ask. Students, do you have any questions? Okay, then let me share my Excel window. Say we have three factors. Now I am explaining this evaluation using mixture design only, and the reason behind that is there is one special thing involved in the mixture designs that also we will discuss at present. So 1 0 0 0 1 0 0 0 1 0.5, say yeah, 0.5 0.50 0.50 0.5 0 5.5 1 by 3 1/3. Okay, these are the experimental runs. Now we will have also interaction terms x1 x2 x1 x3 x2 x3 and x1 x2 x3, and there is a response y. Say I'm arbitrarily writing the response over here. It is 10 15 20 25 30 35 and say again 30. Let's okay. These are random and will not focus on the values at present. So now, or let us put the values from the experiment which we were calculating. Okay, so that it will be easier for us to work with it. Let me place the values from here only. So 6.1, 7.5, 5.3, 6.6, 6.4, 6.9, 7.3, and 7.2. Six point nine, 7.3. Okay. Now here I'm replicating this design. Replication means repeating. I'll explain why I'm replicating, because sometimes it may be problem with the calculative part. There is a problem with the Excel, that when the number of columns and number of rows are equal, the Excel will not allow you to go for regression. Let me show you with an example. Here for analysis, we will use regression analysis. So you need to go to data, from that data analysis, and from data analysis, regression analysis. In regression, it will ask you for input Y range. So at a time, we can input maximum one Y, maximum one dependent variable, but there is no such limit for independent variables. So we can input n number of independent variables. So here I've selected all the X variables, that is x1, x2, x3, x1, x2, x1, x3, x2, x3, and x1, x2, x3. Okay, here we are marking constant is 0. Okay, pick the constant is 0 because we don't want the constant over here. B0 is not required in a mixture design. We will provide the output range. Now, when I press the OK, I'll get an error message. What error message is that? The input range contains non-numeric data. Sorry, that is first, I think I forgot labels. So now labels. Again, an error message is there. The number of rows and columns in X range cannot be the same. That is the major problem with the MS Excel. If there are less number of rows, experiments than the variables, then also it will give value, but without the confidence. That is, it will not provide the probability values. So what we need to do is we need to select now last experiment which I have replicated. Okay, and that replication was for purposefully. Now we will get the output. This is my output. Now if you look at the output, it is showing r square is equal to 1. Multiple r is equal to 1. Technically, it cannot be possible that we are getting exactly 100% correlation coefficient. Your r square should be as close as possible to 1. But practically, we will never get is equal to 1. So if it is 1, it indicates there is something wrong with your calculative part. Now, these are the coefficients. When let us first focus on the Anova table. So this Anova table, the F calculated value is very, very high. Okay, the Anova is similar to that which we were preparing, but this is a factorial Anova, and it will give the F value for the entire model, entire relationship, and the coefficients which we are getting are over here. So the coefficient of the x1 is 6.1, that of the x2 is 7.5, that of the x3 is 5.3, and so on. So the mathematical equation will become y is equal to y equals 6.1 times x1 plus 7.5 times x2 plus 5.3 times x3 plus minus 0.8 times x1 x2 plus 2.8 times x1 x3 plus 2 times x2 x3 plus 15 times x1 x2 x3. Okay, so this is the mathematical model relationship which shows the relationship between our independent and dependent variable. Okay, it shows the relationship between independent and dependent variable. Now using this equation we can predict the response. Let me show. in a previous design, the experiment was performed at 0.5, 0.25 and 0.25. Okay, 0.5, 0.25 and 0.25. Checkpoint batch, which was shown in the presentation, was having this value, this variables, and the response was 7.2. Let us try to predict it, whether it is correct or not. So let us find out the y by calculation. So it is equal to 6.1 multiplied by x1. Okay. Plus 7.5 times x2 plus 5.3 times. Are you getting it? If you have any question at any point of time, you can ask. Minus 0.8 times x1, 0.8 times x1 multiplied by x2 plus 2.8 times x1 multiplied by x3 plus 2 times x2 multiplied by x3 plus 15 times x1 multiplied by x2 multiplied by x3. So the value obtained is 7.09. It is close to the practical value. Practical value obtained is 7.2. Okay, we can also find out the percentage deviation, that is equal to the 7.2, that is the predicted, practical minus predicted, multiplied by 100 divided by the practical value. So the deviation, percentage deviation is 1.47, and that is acceptable. Okay, it is, if it is less than 5%, we can accept it. Clear? So by this way, we can perform the regression analysis, and using the regression analysis, we can get the idea about the relationship between our independent and dependent variables. We can predict the response at the points where we have not performed the experiments, and by preparing checkpoint batches, we can confirm that whether the relationship is correct or not. Now, one more thing you need to remember is this p-value, probability value. Ideally, this p-value should be less than 0.05. So it provides the 95% confidence. If the probability p is greater than 0.05, it indicates that the effect of that factor is not significant, or it cannot be utilized to predict the response properly. So your p-value should be less than 0.05. If some variables are having probability value greater than 0.05, we may go for the reduced model. That is, we can again conduct the regression analysis omitting those terms. Say for x1, x2, for an example, it is less than greater than 0.05, then we can omit x1, x2, and we can again go for the regression analysis. Clear? Any question in this, anyone?
No, sir, clear.
Okay, then. So we are now, let us analyze one factorial design. Okay, x1, x2, and x3, and x1, x2. Wait a minute. Let me copy it. Now, in a conventional design, we have the design like this: minus 1, 1, minus 1, 1. Okay. Now in the same design, I'm putting some response. arbitrarily placed the values over here. Now we need to go to data analysis, regression, input y range. This is my y range. Input x range. I have to select the entire x range. Labels, constant is 0. Now I need not to check the constant is 0. Okay, so constant is not 0 over here. Now here also I'm getting r square is equal to 1. So that is the problem. Now look at the p values. I'm not getting any of the p values or any of the f values over here. Okay. The reason behind this is the n-1 rule. We can get maximum n-1 coefficients. Maximum n-1 coefficients with confidence. Though Excel will provide you the values but not the confidence, and the confidence is obtained from the f value and p value. F means the f calculated. It should be as high as possible, and probability p should be as low as possible. If we are not getting these two values, we cannot rely upon this relationship. Mind well, we cannot rely upon this relationship. So the data are without confidence. So we need to take care that we are at least having sufficient number of experiments. So again, I'm repeating one experiment over here, replicating one more experiment over here, and now we will go for the regression analysis. Data analysis, regression, and increasing one value. Okay. So now I'm getting the confidence. Look at the output. There is a okay. So now we are getting the r square value, that is 0.9997. It is close to 1. Our f value is 512. That is sufficiently high. It should be at least in 3 digits. It should, if it is in 3 digits, it is good. And significance f, this should be less than 0.05. It should be less than 0.05. So it shows good confidence. For p value also the same things apply. P value should be as low as possible. It should be less than 0.05. Now there are few factors in which the p value is greater than 0.5. Say these are the factors in which the p value is greater than 0.05. Sorry. For x1 also it is greater than 0.05, but normally we cannot omit the main effect. So we need to go for regression again, omitting all these terms which are insignificant, which are having less relationship. So again we can go for data analysis, regression, and we are omitting the x which are insignificant. So only x1, x2 and x3 are having significant effect. That I am including, rest I am omitting. And I'm getting new output. So here my r square again is 0.99, less than the previous one. Obviously it will be, because as the number of variables decreases, the r square decreases. Okay, wait for a while. Okay, again the one here. The f value is again 301, that is less than the previous one, but still it is significant, and all the p values are less than 0.05. So now this equation I can utilize for calculating the response over the response surface or over the experimental domain, where coefficient of x1 is 3.18, b0 is 28.93, coefficient of x2 is 5.93, and coefficient of x3 is 11.43. Clear? With this, we are ending the regression calculative part.